artificial intelligence. So it's not the same thing. You have more subfields inside of artificial intelligence, like robotics and fuzz logic. So machine learning, it's a subfield inside of it. But most important, it uses techniques to learn from the data and make accurate predictions. So the whole point to use machine learning is train over like some specific data and do predictions in new data. In the field, we call it like a generalization. So you receive new data that the model didn't see, and you produce good predictions. And there are several ways to implement it, different algorithms, but in essence, it is. And other important part is without being explicit programmed. So if you think what is happening inside of machine learning model, you can code, like hard code all these rules. So if you think like a developer, I could get an image and do a lot of rules myself to try to identify, for example, where is water, and work with the data, try to find some values, and I can code that. But if you think in the way that machine learning do, it implements it for you. So it will create all these parameters, look in the data and try analyzing the data and try to establish it like automatically. So without being explicit programmed. So if you think in the artificial intelligence field, you have other subfields. So machine learning is one of these subfields. And inside of machine learning, you have like other buzzword today, like deep learning. So here we will not talk about deep learning. So we could have other session about it, but we will use TensorFlow. So it's not every time that you use TensorFlow that you implement deep learning. But, and today all these concepts are kind of mixed. So for example, in the artificial intelligence, you have like a natural processing language subfield. And today you have pretty good algorithms and really accurate algorithms in deep learning to deal with that. So some of these subfields are really changing too much. And the deep learning, it's a really hot field in the research. And there are so many algorithms and really nice implementations of it. But mainly when we are talking about deep learning, we are talking like processing graphical card interface, processing unit like GPU, convolution neural networks, and all it's more related with it. We have like a recurrent neural networks also. But here at the end of the training session, we will use a regular artificial neural network combined with random forest and with the gradient and clustered trees. So in this session, we are actually inside of just of the machine learning, not actual deep learning. So now, if you think in the machine learning, you have mainly three like categories about algorithms. So we have the supervised, the unsupervised, and the reinforcement. So the supervised, it's mainly when you provide like training data, and using this training data, you already provide like the answer. So you need to have like raw data. Can be image, can be text, can be a table, it doesn't matter. But you need to label this data. So what it means that you will look this data, so some human being will look this data and it will create like what is the expected result for this data. So if you think like in an image, we need to provide for the satellite images where are the classes that we want to map or the values that we want to map. So for example, you could provide like coordinates, points, specifically on top of the image showing that this is a pasture, this is a conifer forest, and things like that. Or you could provide polygons also. So, but you need to provide it. So you need to have a data with label so label data, to do the training, and the machine learning will try to match and to analyze all this data to provide like an expected result, and you can compare with that. So here mainly we will use it. You have the unsupervised learner. It's more like machine learning. So you don't need like training data, and you can work with the raw data and try to find some like hidden structure on it. So for example, for the spatial classification, you could try analyze purely the values of that image and try to aggregate values that are similar. So if you think maybe a pixel in a forest, it's in a specific part of the image, it's close or it's related, has values related with pixels on other part that are forest also. So it's possible, but sometimes the most part of the times actually they are not really accurate. So the accuracy, it's better if you have the label data, but there are researching, there is a lot of research in this field also. And you have the reinforcement learner. So machine learn, this reinforce, you learn by mistakes. So you have like actually an agent that try to do something, and you have some way to measure what to analyze if that action produce or not the expected result, and it will learn considering the response of different attempts. So I'm not familiar with this approach, and you can combine it. So you can have like a supervised learner, and you can after that you can have like a reinforcement learn. But it's important to be aware of these fields and these concepts. And here, mainly we will work with the supervised machine learn, specific classification algorithm. So we are not doing regression. And if you think in a classification, the difference between classification and regression, mainly we are producing like factor values or like integer values or class values. And in the regression, you are the model will predict like a continuous value. So it's more like to predict some variable. So in our case, the land cover, it's actually like a class. We have the same, exactly the same value. It's an integer, but we have the same value for different pixels of the images. But for example, if you think if we could train a model to predict the precipitation, for example, and to predict precipitation, the output will be like a continuous value. Each pixel could have some level of the precipitation, and this is more like a continuous value, and you need to use a regression to implement it. So, and the other part, it's about the programming. So inside of the model, you will have like what we call like the parameters. So the parameters are actually how the model will implement all these rules, all the trained rules to split and to analyze the data and predict the expected result. So to predict if that pixel, it's a class. I'm talking about image, but for example, you can do the same thing for text. So nowadays, for example, the Google Translate do it. So it analyzes the whole structure of the text and predict the output as a new in another language. And it's mainly it's the same concept. So you have the input data set, it's actually text, and you are predicting, and the Google Translate predicts it as a text, but in other language. And if you think in the way that it was implemented, anybody created like anyone created some hidden rules inside of it. The model learned it considering millions of training data in the case of the Google Translate, but you can have it for different kinds of applications. And one important concept is when we are talking about the model, the parameters are like, we train the parameters. So if you think in the random forest, it's basically a decision tree. So you will analyze the data, and this data could have like 8 10 features, 10 variables. In our case, it's 10 images. We will use 84, but could be like any number of covariates and features, and analyze this picture, these features and these pixels. The model will train like a tree, and each part of this tree, it's a decision tree. It will like try to divide this data to classify in pasture, in coniferous forest. So the way that this decision tree is created, this is like specifically the rules. These are the parameters. The hyperparameters are mainly they are related with how you control the learning process. So for example, if we use 100 trees or 10 trees for the random forest, this is the hyperparameter. So number of trees is a hyperparameter. Inside of each of these trees, we have parameters that will analyze the data, and it will split it and we will generate the output. So this is the parameters of each learner. And different algorithms, they have different parameters, but mainly what you need to remember is the parameter, it's actually, they are learned from the data. So, and it's automatically derived considering it's a data-driven process. So you don't need code anything inside of it. You just need to code outside to control the process. So this is a expected machine learn, supervised machine learn approach. So we have some raw data. Using this raw data, you can have features. Again, this could be anything, tables, text, images, doesn't matter. And you have labels. Labels are like, what is the expected result considering this raw data? And of course, the raw data, you can derive just some features. You can have like a bunch of raw data, but just part of it you are using to do machine learning. And you have like the model training and the model evaluation. And with a trained model, so after the training, you have like a model, a trained model, you can save it, you can load it, but mainly you can use this trained model to do prediction over new data. So all that effort creating the labels and create the expected result, it needs to be currently, actually, it needs to be done by someone, so a human being and me, and you can use it to predict and to generate predictions. So this is the expected workflow, but for the real world applications, we have more something like that. So it's not so beautiful, but you have, when we are talking about real applications, you have like a way more complex, for example, data and raw data than these benchmark data sets. So when I'm talking about benchmark data sets, I'm saying like if you download, for example, the TensorFlow, you have like some digit numbers, like images with digit numbers, and they are really organized and pretty and ready to go. So you just need to get this data and do some predictions, and you already have the labels. But the most part of real applications, they don't have the data really organized like that. And you need to prepare the input data set, you need to prepare the labels, you need to prepare this expected result, and you need to work with all the modeling part, but at the end you need to do predictions. So otherwise you are not interested in just create a model and use this model to predicting just a portion of the data. What is the end goal considering a real use application here? And for example, in our case, the end goal, it's really mapping the land cover classification in the continental Europe. So we did all this effort, but at the end, we need to predict it. So we need to get this model and really scale it up and predict all the pixels of Europe. So there is a way more complexity than just like a simple workflow. But mainly, if I could like put two most important aspects. You need to prepare the data before to really start doing modeling, starting doing machine learning, and you need to be aware what you plan to do with the final model. So what will be your prediction strategy? So you can put it in a, I don't know, in a service, and the users can access this service as, for example, we have for the Google Translate. It's a service for a machine learning model, and everybody can go there and just put some text and it will translate. So considering a real use application, you need to be aware of how you will serve your predictions. So you can do all the predictions in-house as we are doing, generate the maps and put it available to the people who use the maps, or we can really serve the model and to the other users really access and do new predictions. So there are several possibilities on it, and it's important to be aware of these possibilities. So, but let's back to our simple example, and we can expand it for the geospatial data. So now, if we specifically explain it in the context of the geospatial data, this is more or less the pretty way, I say. So you have like the raw Earth observation data. So this Earth observation data, as I was explaining in the morning, so you can have like the Landsat data, Sentinel data. There are a lot of satellite images available, but you need to download it, you need to organize, you need to remove the clouds, you need to do several pre-processing steps and to produce an analysis-ready Earth observation data. So, and using this analysis-ready Earth observation data, you actually need to provide now the labels. So what you want to classify in this image. So you want to classify like soil organic carbon, you want to classify land cover, you want to classify, I don't know, just one class, pasture maybe, or you want to classify water. So you need to provide the labels because the performance of the better models that are available now, they work with supervised classification. So you need to provide the samples, the training samples. And the training samples, it can be like points, lines, polygons. It doesn't matter. A sample, it's just like a vector that you will overlay with the data, get the pixels and put inside of the machine learning. So here in the training session, we will show the like overlaid data, but in the EU map, so look at, did talk about it. In EU map, you have like the functions to, I don't know, get one point, that samples that you collected in field, for example, and overlay these points over like raster data, different raster layers. So in these training sessions, we already did it. So we will work just with the overlaid data, point data, that for each point we extracted all the pixel values. So, and considering it, we will train model. So we need to train a model, we need to evaluate this model. So there are some strategies to do it. And after that, we will have like a trained model. And when I say like trained model, it's a ready to go model. So it's a model, it's a file, it's a model that it will able to do predictions without do the training again. So we will show it for you in the code. So mainly when you do the training, you have like a model, and this model, he has like, he knows how to process new data and predict like the land cover. So, and it did learn considering just the samples, but you can use to do predictions in different parts of your data, of course. So there are some limitations with that, but the end goal is you really, for example, train a model to do the prediction in the whole Europe. So as we are doing here, and you can load this model and you can skip all this training process and just predict. Yeah. So if it's straight going, and that's the idea that you will be able to process analysis rather than raw. No, that's a good question. Yeah, actually, you need this rule, this arrow here. You need to read from the analysis ready data. So because Yeah, I will fix it in these slides. Thank you for noticing it, because the training, it's really sensitive. So if you change a bit the pixels, you change completely the predictions. So there are some techniques to really try to put, like, you can simulate noise in the analysis data to try to predict raw data, but it's a different type of research. And here we are predicting analysis ready data. So this is one example. So I did it in my PhD. So I worked in Brazil using the Landsat data. So mainly we had like more than 30,000 points for each year, and these points were visually interpreted by 3 specialists, and they classify it as pasture, forest. And they are, you can see the points here, they are really spread all over the country. So this is and in my PhD, I was part of the GIS and remote sensing laboratory in Brazil, and actually we generated this data from scratch. So here we actually develop all this. We develop a sampling design, we spread the points all over the country, and we develop a solution to help the specialists to check the pixel values and see if it's pasture, if it's crop, and things like that. So in this context, it's not like it's really specific, but what it's interesting here, we have samples for the whole country and for all the years. And it's not the main part of the applications. So, but even so considering that we have points for all the years and for all the country, you can see here these little squares here are like, those are the Landsat scenes. So we have 308 tiles, Landsat scenes, to cover the entire country, and we have 34 years. And what we did here we trained one model per each scene. So if you think in the machine learning way, the training process occurred by each Landsat scene and by each year. So at the end, we trained more than 2,000, almost 13,000 random forest models, and we mapped individually all the years. So, but if you think we have all this data, so it would be possible training one single model. And what I mean with that, I mean, I can get all the points from all the years and for the whole country and put all these points in a single machine learning model and train it. So it will be millions of points, but maybe it could produce a better result. But there are 2 problems with that. We need to have the capacity, software and hardware, to do it. So it's not easy to train a machine learning with millions of points. And we need to have harmonized data. And if you remember in my first, in the morning, I explained that if you work just with the raw data, with the Landsat, we have 3 sensors. These sensors are different. So one image of 285 will not have the same pixel values, the same reflectance values from like an image of 2020 accurate by Landsat 8. So you need to work with harmonized Earth observation data. So, and there are 2 products at least, probably there are more, but the main products to do it, it's the GLAD Landsat R&D. I talked about it during the morning, and there is this other product that combines Landsat and Sentinel-2. So, and produce like one harmonized data cube, but it's just with Landsat 8. So we will have just since 2013, but I think they processed it just from 2015. So this is mandatory to try to create one single model for all these, to classify, for example, multiple years and different parts of Europe. So in the OpenDataScience Europe, we are doing it mainly. So we took all the Lucas points, that it's basically a a well-known field survey here in Europe, and we combine it with some generated points from the other land cover maps, Korean land cover classification, and mainly we are using all these points to train one single model. But it's important to emphasize that we have the capacity to do it, and we also have like a harmonized Earth observation data as the GLAD Landsat R&D, and without gaps and all these parts that I was explained during the morning. So at the end, we are predicting dominant class, probabilities, and uncertainties. So in the end of this training session, part 2, you will produce it also in the Python notebook. But we are also using more than one learner. So random forest, it's already Ensemble learners, because inside of a random forest, we have several trees, so decision trees, and it's why they call it like a forest. It's multiple trees, but we are also using the gradient boosted trees and the artificial neural network. So we will show how to do it in Python for the tiles that we prepared. And yeah, now it's time to go to the code and start to really do classifying the land cover considering the data that we prepared. So just to an overview of what we will do, mainly we will train a regular random forest, pretty straightforward, without any type of hyperparameter optimization. It will be just a purely random forest, and we will predict it to see how it works and to understand how UMap is doing it internally. Later, the second example will be the random forest with hyperparameter optimization. So you can test different combinations of hyperparameters to really predict it and benchmark all these different parameters and find what is the best one considering some evaluation metric. And in the second part, we will train the random forest with probabilities. So if you think in the random forest, you have multiple trees. So each tree will produce like a output, and you can use this output to derive like a kind of a probability. So, and this probability, it will it changes completely the output of the algorithm. So we will see it, but instead to just have a hard class, a dominant class, so it's pasture or forest, you can have like multiple probabilities, and these probabilities will show, for example, maybe there is an area where you have like not a high probability, you can have a high probability just for one class, so you have sure the model is pretty sure that this is, for example, coniferous forest, but you can have like other pixel where the coniferous forest is 60% and the broadleaf forest is 40%, 30%. So there is some confusion there. And if you think in the image, then it kind of makes sense because you have some limitations with the data that we are working. It's not possible really get one pixel and have 100% sure that inside of that pixel we have just one single land cover class, because we can have in a transition zone, so there are several complications of it. And at the end we will expand this and put more learners, so more tree learners, and explain how we are deriving the uncertainty and how we can improve the result. And this is actually our current workflow. The code that we will show here is actually the same code that we are running in our servers to produce the land cover map available in the OpenDataScience Europe. So now I will pass the floor to Chris. I don't know if there is any question for this introduction. No? Okay.
Should I take the microphone?
Yes, please.
Thank you. All right, let's have a look. Okay, who got the virtual box to work? Oh, am I unmuted? Can you hear me? Oh, good. We're all set. Okay, thanks, Leandro. So I will show you a little bit of the code, and we'll see if you can also replicate some of this. Who is able to also join me with the code in the machine, in the virtual machine? 1, 2. 2 people. Okay, so for the rest, I will just show the code, and then in your own time, you can have a look if it's also applicable to your projects. So this is the Jupyter Notebook that we will look at today. And then here we see the example of the interface, the online interface that we use to also make it publicly available. And here we have the reference to, because much of this work is from Martijn's work that's also here, which will soon be publishing on this as well. So that's also interesting, I think. So first of all, we load the main packages that we need. I will reset the kernel so you can see how it's working. Should be working. Let me also clear the outputs. So first, oh, is there anyone here who worked with sklearn libraries before? No one. I think I know some people who did. That's okay. Okay. So you'll be recognizing some of this code here. So we will be loading the EU map package, which is also, as Leonor mentioned, the main package that the current workflow that we use for the data that we provide. And we use some standard libraries, something to find our files in the system, and to load these files into the environment. So let's load these packages. Then I will define the tile that we use. So we provide 2 example tiles that you can try. And I just run this to be able to find the data on my drive. So here we have the file system, and I put the directory of the data. So that's this directory. Okay, so let's run that. Then I have some training data that is here. It's a geo package. So that's basically a lot of these points that are mapped, we know, okay, this is this land cover type. That is all put into this database. And then we will load it using the GeoPandas package. So now this data is loaded into the variable called points. So here we see just a regular table with yeah, all the information. So here we see for this point, we know the class is 112, and then this is the value that this is the distance to the coast. This is the weighted distance to the coast, I think, that Martijn developed. But also, if we look further into the data, then we see the Landsat values, and also the names and the survey year. And because this is georeference data, so we here see geometry. And the nice thing for the GeoPandas package is that we can also see what reference system is used. So this is just GeoPandas data frame that has these functions to find all this information. So here I can actually see what my reference system is for these points. Because if I look at these values, it's not a regular coordinate. So here you can see how should I translate this if I want to plot it in another kind of software. So then I want to get some information about my data. So for instance, so I just make a kind of a bar graph about some of my values. So here, for instance, I have the class name and the survey year, and then I want to see how many points do I have in my training data, just to get an idea of what I have here. So I have a lot of coniferous forest points and moors and heathland and agriculture with natural vegetation. And here I see when these points were measured. So I have most data in 2018. So knowing this, we can, generally I would do a more in-depth look at these data, but for this presentation, I will just go ahead with looking at the random forests, and then I will focus on doing just the spatial, and then Leandro will later also include the spatial temporal. So then we will see. Huh? Oh, I'm using all the years. Okay. So I will look at the spatial temporal data actually. So here I'm also including some sklearn functions. So this is actually to do. I think we use, yeah. So this is for a bit later where we use the hyperparameter optimization. I'll come back to that. Then the random forest classifier, that's one of the classifiers that's included in the sklearn package. The sklearn package has many types of classification algorithms, and they're all kind of standardized. So we try to also enable you to use all these different classifiers, which makes it really versatile in how you can use it also on geospatial data. So I think that's a very cool feature of this package. And this is the k-fold, that's to do an amount of folds on your data to get an interesting evaluation metric. So here I will initiate the estimator, the random forest estimator with 5 estimators. I'm going to select points just from the tile that has my tile ID that I have defined before. And I will use a 5-fold cross-validation for the training. And then I define all the variables that I want to use for my training. So in my data set, all the columns that we saw, I will put the prefixes for all these columns here, so that I know which variables I'm using to train my classifier. So this is something that was written into this package, so you can really be quite sure about what you train on and and it's easily configurable. And then the target column, that's our land use class. So I will load the landmapper class with all these configurations. So I have my points data, my data frame with all the training data. I have the variables that I want to use, so it will be selected from this data. Then the target, so what should be trained on, and then the estimator, the class that will handle the folds, and another parameter where I just select classes that have enough training points. So I'm just going to look quickly at this one. So it will select only the classes that have the highest amounts of training samples, because for these ones we cannot reasonably think that we can make a good prediction because we don't have a lot of training points.
Can I just explain it? Because
sure.
We included this parameter because when you do a cross validation, you need. I think I need to.
You want to have a look?
Yeah. No. That's
okay.
So when you use like this parameter, it's important because when you do a cross validation, mainly you will divide, like imagine you have all these points, you will divide in 5 regular groups, but you need to have enough validation points in each of these groups. So I don't know, maybe you have just 1 or 2 points for some class, and these points will be present only in one of these folds, in one of these regular groups. And sometimes some algorithms that doesn't manage well with that. So you have like you need to provide, depends of the algorithm. You can classify with less amount of samples, but for example, I know that SVM has problems with that. XGBoost also has problems with that. So there is a limitation with the way that the validation, the cross-validation is implemented, considering these regular folds, because you need to have all the possible classes in each of these folds to do a proper validation.
Okay, thanks. Yeah, and then we also focus on that it's usable in a production environment. So maybe sometimes you don't want all the outputs to be printed to the terminal or whatever, and then you can also put you can switch off all the outputs. So that's also a useful feature, I think. So let me see if I run this. I run this. So I will run this block of code. So I get some information about what the land mapper is doing. So it's removing some samples because it doesn't comply to this condition that I specified, as Leandro just explained.
You can just explain that this is actually the percentage, right?
The percentage.
The percentage, yes. Yeah, it's the percentage considering for each class. Yeah, just back to that plot, that just because I think it's easy to.
This one.
Yes, just yeah.
So it's if they are less than 5% of the total of the samples, they will not be selected. Yeah. So these are less than 5% of the total of all the samples that we have. And then, so these are the original classes, the numbers, and then they are remapped to this because some of the packages in sklearn, they need us to have, they cannot handle these kinds of numbers to do classifications. So then we will train this one. I'm putting this number so that we have the same selection of folds for our training, so we can have a bit similar results if you run it on your own machine. So then I can look at the accuracy. So here we can see all the accuracy metrics. So we get a 56.6% overall accuracy, and then for each individual class. So if you want to know which one it is precisely, you can have a look here how they are mapped. And we will also print a confusion matrix that will show us some, but in a bit more visually appealing way. So here I'm just creating, because all the names are in the data that we provided. So I'm just creating a dictionary to translate the number that's mapped to the actual name, so it's still understandable to us. So here we can see the true classes and then how the model is predicting them. So for instance, let's see, sports and leisure facilities are confused with broadleaf forests sometimes. Or yeah, that's happening sometimes. So this you can use to get some information about how your model is performing, and maybe where you need to see if you can do some feature engineering to increase your accuracy for specific classes. Let's see. So then you can also access this in a tabled way. So what you expected the class to be for every prediction that we did. So then you can generate any type of accuracy metrics that you would like to do with your own functions. So after training, then we can save this model, so we can use it in a production environment or something somewhere else where we don't have to retrain it every time. So I'm just going to save it to this this file. So we can find it here. So it outputs where the location is. So I'll show you where it is. So this is actually my model now. So I can actually just put it on in somewhere, send it to someone, and he can also try do predictions with this same thing using the EUMAP package. And now I'm just gonna reset the kernel to see if I can actually load and do predictions again with the same model. So I have to reload all these packages because I just killed the whole instance. And then I'm gonna define the parameters again because everything is gone. And then here I'm gonna load my model again. So this into this variable. And then so we prepared all the data into these directories here that Leandro just talked about. So some timeless layers, and also I won't open it because it's many files, so it will take some time. But there's a lot of Landsat, all the Landsat bands that Leandro just explained for every season, for every year, they're all in here. And for all the quantiles. But these two functions, they will find all the paths for a specific year that I want to predict. So now I'm just going to predict 1 year. So I will find all these layers here. I just print 5 of them. So for 1 year, I have, let's see, I put them together so I can import them into my class, into the land mapper. So I have 86 variables for this prediction that I need. So that's just I have all the paths to all the variables that I need in this variable. And then I need to rename them because the original ones, they didn't have a year there. So now I have in every name, in every data that has a year component, I have the year also in there. So I want to only get the 2018 data. So I will replace the year with 2018. So I can rename all these files so so the model can find the right data to predict on. So it loads the right files to do the prediction. So here I put all these parameters into the model. Now I'm not interested in the output. We just looked at it. So we're not interested in how the renaming works because it's a long list of names that will be replaced. So it's a bit. I can show it actually. That's a good point. So let's see what happens if we show it. Makes more sense actually. So you see what. So here we see that the original name that I had in my model for this variable, it was this one. So it has no year component, but I want to find this one where it says 2017. So that's what this function did. So I make sure that the names of the files are right. So this, yeah, it's a general thing in I think machine learning to, you have a lot of preparation on your data. So this is how we help handle the preparation of your data and keep it kind of comprehensible. So let me do that one more time without. So we have one output, I think. So now it's doing a prediction. So it took about 1 second. So here's my output. And I can plot that output with also one of the plotting functions that we provide. So here we see what the classification found based on our training data and the model. Let's see if we can find that one, if it makes sense to us. So here it is on a map. So here we have the Netherlands. We are now right here. Let's see, where are we? Here. I think. This is us. We are here. Right here. Okay, so let's see. What is it? So we are value 0.
7.
7? Ah, yeah, 7. Okay, so we are 7. So let's see what it is. If that makes sense. Pastures. Well, we tried. This was our first try. Okay, so let's see what this is 0. So that's moors and heathland. Okay. So this can help you kind of see, you know, what's happening with my model. You have a question?
Yeah, just about the training sample and theory some filter to cater for the spatial order correlation. Have that in your
Yeah, we have it. If you open the documentation of the land mapper, please. Like, but actually, we have like because all this package, it relies on the functionalities of scikit-learn, and inside of this scikit-learn, you have a validation strategy that use like a group ID to split the data like in a way that will avoid the autocorrelation, the spatial autocorrelation. But open the API reference, please. Mapper. Yes, land mapper. So you have this CV group column. So what we will do in our production work, we did that. So all the tiles that I presented in the morning, so they are like 30 kilometers by 30 kilometers. So we use it like the tile ID as the group column. So to do like the spatial, the cross-validation, it will be like a sort of spatial cross-validation that will use this ID. So it will avoid, for example, train a model with samples from one tile and validate with samples of the same tile. So, but it's just like you need to change the CV to group fold. So it is implemented in the scikit-learn. What we did was just like a integrate to these functionalities.
This one, right?
Yes.
So you can use this one. So now I use here somewhere. Let's see.
You just use because here we are just using, for example, it's just one tile. So we could split these points in like subtiles and create this blocking structure. But for this example, probably it will work, but we need to really define this in the data frame. But that was an excellent question.
Yeah, good question. Thanks. Let's see. Yeah, so in here, I think you can see, yeah, now we select on the tile ID, but you can then use it to do a spatial cross-validation. And the nice thing is that, so all these things, you can use them within the package, right? So you can, now we use a k-fold, but now we spoke about this grouped k-fold, but you can apply different kinds of strategies here. Does that make sense? Yeah, great. Okay.
You can show the models also.
The models?
Yeah, in the scikit-learn.
Let's see.
The API.
I think, where are they? Let me look for the
API.
this one. And
Yeah, so you have, because these libraries, they create like this base class, this base estimator. So all the algorithms that are implemented here, they have kind of the same methods. So our package actually use all these methods, training, predict, and things like that. So for example, you have like the SVM. So if you replace the random forest through SVM, you will have the same structure that we are showing here, but with a different model, with a different learner. I think on top, on bottom, you can see that there are some. So you can use like a linear regression. So we will use more learners, but it's fully compatible what we have here in the scientific level.
Yeah. And I think you will show an example where we use multiple learners to do ensemble machine learning. Okay, so we have now looked at this example. So our first try, we didn't do any hyperparameter optimization. We just train a very simple model on our training data. And then now we will try and do some hyperparameter optimization and see if our results are actually better. So we already saw this one. So this is also sklearn functionality that we will also use. Then the rest, this is kind of similar to what we did before. But here we define our grid search. So we will run over the different parameters that we want to test. So we have the maximum depth and the maximum features and the number of estimators. So we want to test all these combinations of parameters. And the rest, and we use F1 score. That's also a standard scoring in the sklearn package. But here we can also define our own. I think we will do it a bit later. And we just input the estimator. And then the only thing we need to do here is just add the hyperparameter parameter, and that will allow us to actually do this grid search. Let's see if we can do this. So we get the similar output, and then now we will train. We'll actually train the model 90 times and see which one is best. So that might take a little bit of time. Let's see what the computer is working on it. Some nice green bars. That's cool. So it's still running. So now it's almost done. I think it's done. Yeah. So now we can see if the prediction is actually better than before. So we have, what is it, about a 6% increase, I think, in accuracy. So it's something. It's an increase, so that's good. Then we will do the same. We can plot the methods to do some interpretation of our results, and we can look again at our results. We can save the model again and load it again. And I think, did we get an output file or not?
Yeah, you can try to do the prediction.
No, okay, we skipped the prediction. Okay, but we can do a prediction, but let's have a look first at the probabilities, and then we can have a look at also these files. So now I'm using a log loss scorer. So this is an example of a custom loss function that we make. We also use the sklearn implementation of this, adapted to our case, and we do the same thing here, but here we also tell our class that we want probabilities. So because we use this random forest with a lot of different predictors, we can see if they are corresponding to each other or not. And if they are all pretty sure about the class, then the probability is high, and otherwise the probability is low. or it could be lower. So we make a prediction again. And let's see if there's different results. We need to train it, of course. So now we use a different loss function. So we will, it's a bit different to compare it. So here we have now our accuracy metrics, but then geared towards the loss metric that we defined for each class again. Let's see. So that's, so we get from the model, we get different types of accuracy metrics that we can all access through through these probability metrics variable. Let's see. And then we can also print them. All right. And then we can see if this loss function actually gives us better results by looking at the prediction result. So now I'm applying the same function, so to predict with the layers. But here I'm putting all the years. No. So now we're still looking at just 2018. So here's the same function to find the right data and to put all that together. And then we're loading it into the LandMapper class and producing a prediction, but now not just the class, but also the probabilities for the different classes. And we also provide the plot raster function to actually have a look at the results. So yeah, it's of course a very rough interpretation, but if you look at this one compared to the other one, let's see where it is. You see it's a bit cleaner. It's not sure if that's better, but at least you can visually appreciate the difference in the result. If it's better, that's of course a matter of further interpretation and looking at the data. But now we have a bit more at hand to actually do these interpretations. So we can now also have a look at the probabilities. So I think these are related with, so 1 is related with 0 in this case. Yeah, okay. So anyone interested in anything in particular that we can look at?
Let's see if it works.
Hello. Seems to work. I'm sorry, we have an issue with the microphone. Can you hear me? Is it okay? Yeah. All right, let's use that. Okay. So I'm now trying to visualize the probabilities for the moors and heathland that we just produced using the LandMapper class. So here we see the probabilities for this area. So again, this is where we are now. Let's see. So this is the Wageningen area. This is Wageningen town, and here is the conference center. So now I can have a look where it's likely to have moors and heathland. Yeah, let's have a look. What's this? So this is actually airport. So at least now we can see what areas have impact on our predictions. And I should actually, what I like to do is, because it's still the easiest way to compare these things, to go to our viewer and see. You can also see the Landsat data over time. So that actually gives us a lot of information on what it is we actually see in our training data directly. And then you can, yeah, it's not, you can probably also load it in GIS, but this one is like really, I think, really user-friendly to go to different years. Let's see. We have the.
So it's a base layer. So
Okay.
I go to the first item.
This one. Yeah.
The last one.
That's it. So here we can have a look again. And now we have the layer coniferous forest. So let's have a look if this is corresponding to what we found. So here we are. Yeah, it's a tricky class because it's very much like, I think, many other classes. But yeah, hopefully our model also picks up these other classes and actually produce higher probabilities for these, so that even though we see high probability here, maybe other classes still have higher probabilities there. So let's have a look. We now created our own prediction here. Let's see. Let's stay close to where we know where we are. So this patch, for instance, it's different. So now I'm observing that our predictor kind of finds a patch of heathland here, or at least a higher probability than that we have found in the prediction code that we used for that we used for this. So that's interesting. I think, you know, this is just some interpretation of the results that you can do. And I think all these tools, they really help you with visually interpreting also your results and see what you find in your training data. So that's very interesting. Let's see where we were. And you can do this for all these classes. So this class 5, for instance, that's coniferous forest. So this makes a lot of sense if I look at this, because if we are here, Wageningen, then this is the Veluwe, that's the biggest forest in the Netherlands. So for me, I think, okay, this is, at least there is quite some truth in this prediction, because I know this is forested area. Of course, there are much more research to be done to confirm this. And then I think, Leandro, you want to show the people the Ensemble machine learning?
Yeah.
Yeah?
Yeah.
Okay.
I can start.
Thank you. And if there are any questions about this part, please. No? Okay.
Yeah, so now we have like the probabilities results, and I would like just to, so Chris show how to execute it, and I would like to explain this report here and the metrics that we generated. So here you can see that you can see this report because Chris instantiated the land mapper with the variables true. So even, for example, for us that we are developing this API and we are using like on a daily basis, it's really important to follow the process. So follow how which part of the workflow it's executing. So these variables, it will like explain everything that happens in the land mapper. So the main points here, it's really you can use all the classes that are available in the scikit-learn. So random forest for learners, but you can also use SVM. You can use a Keras classifier that it's a implementation compatible with scikit-learn. So I will use it, but you also can use it individually. And you can use different types of validation strategies. And here we are just using mainly like cross-validation. So there are a lot of discussion if the cross-validation, it's the right way to evaluate it. But what we decided when we were implementing the library is inside of the library, we will mainly use cross-validation. So if you want to validate your result, you can do it outside. So it's just a matter of have independent points and do the predictions using like the predict points method. So Chris presented the interface here. So you can see that you have these predict points. So if you have like independent points, you can manage it outside. So, and for example, here we are using these Lucas points combined with Corinne land cover, and we are creating our data set. And for the production work, actually, we used almost 6 million of points. So it's much more points that we are presenting here in this training session, because here it's just a matter of how we demonstrate these functionalities. But for example, we have the model trained now, our production model, like to produce the maps that are available now. And we can conduct, for example, an independent validation strategy, and we can spread points all over the Europe and inspected it by visual interpretation, or even go to the field if we have money in the context of the project, collect the actual class of it, and just use these points to do another prediction. So it's a completely independent approach it's not really related with the training and how we are implementing this inside of the model, inside of the land mapper. So you have this possibility, but what it's important here is we are using the cross-validation because it's a kind of metric that allows you to evaluate your training process, how you are capturing the variability of the class, how your features are really like correlated with the expected variable, and you can use this like a reliable way to see if the model is doing a good job. But to provide like a real validation of your result, it's better have like independent data set, and it's better provide like a proper sampling design. So spread points considering like all the assumptions of the statistics, and like a random design or a stratified design to do it. But of course, sometimes you are limited. You don't have like budget enough to collect points to produce new data. So you need to work just, for example, with cross-validation. But in the literature now, you have this kind of discussion, and I personally, I don't believe that a cross-validation it's able to provide like a real and a proper validation for your prediction. So it's a nice way to understand if your model is doing a good job. It's a nice way if you to understand if you are optimizing it, but to provide a real validation, it's better have independent data set. So it's what I presented in the beginning of the presentation. So you need to have no new data. So and you can try to split it, but for the context of the land cover, it's the state of the art sampling design to provide a better validation and a proper validation for your product. So you have it here, not all these aspects, but you have the possibility to use what we trained now to predict new points, not just the raster files, but if you back here, so you can see that considering this cross-validation strategy that we are using here, it's a 5-fold cross-validation. The land mapper, it's actually do an optimization approach to find what are the best hyperparameters, and it's find the best. It's something like vague. So basically, what it's doing, it's calculating some occurrence metric, and here you can see that Chris explained it. So you have here it's a F1 score weighted, and it needs to be weighted because you have it's a multi-class classification. But for example, if you click here, you can see that all those metrics are really available in the scikit-learn. So we could optimize also by the accuracy or by the precision and by the recall that are actually in the context of remote sensing are like user and producer accuracy. So it's possible to do it, but so it's really like it's a modular approach. So you have a validation strategy defined, you have which parameters that you want to test. So all the parameters that I put here, it will be a combination of all these parameters, and you have different strategies also. So I always prefer define the parameters because it's sometimes you really need to think about what not all hyperparameters needs to be optimized, and it depends of each algorithm. So define these values actually force you to understand a bit more about these learners, about these models, and select actually what are like the best, not the best, but the proper parameters that you need to optimize. So in here, we are optimizing the number of trees. So it's something that it's a common standard in the most part of machine learning applied to land cover classification and other domains. But if you provide like, I don't know, 60, 80 trees, so you should have a good result. So considering like a dominant class, hard class. So it's a kind of standard value. But of course, if you put more trees, you will have a higher computation time because each tree needs to be computed, needs to be trained, needs to be predicted. So, and this number, it's actually, it's really high correlated with the performance of the model. So for example, if you have 40 trees and if you have 40 cores, that's not our case here, definitely, we just have 4. But if you have like 40 cores, each of these trees will run in parallel. So the process will be way faster. So it's this hyperparameter optimization, you want to optimize to find the best model, but there is a plateau. So you need to be aware that sometimes you are just adding computational time and it will increase, I don't know, 0.5% in your accuracy. But for some applications, maybe this 0.5, it's really important. So if we are doing like with, for example, medical applications, it's life. So you need to optimize at most, but depends of the it depends of the way and the domain and the application that you are trying to do. So you have this flexibility here, and even for land cover and for geospatial classification, maybe you need to really improve the accuracy at most and process more and with a high computational cost. So it really depends. And here you have like these other two parameters that are actually what is the maximum depth of each tree. So if you think that this tree will like be trained you will split the data set, consider each node of this tree, and this maximum depth will be actually the default parameter here. It's none, so it will grows till like separate all the samples in the training set. But sometimes if you reduce this depth, you will have like a shorter trees, and maybe it could help for the probabilities, because you will have like more fuzzy output, and if you combine all these trees, maybe it will help. But it depends of your model and the way that you are training, and not the way that you are training, but you are training data set. And the maximum feature, it's actually how much features it will be analyzed for each split. So for example, if you put here 0.5, we have 86 features, so it will use half of it to define the best variable to separate the training samples. So, and for example, sometimes I use it like 1 here. It's totally random. So the random forest will be trained like for each tree and each node, each part of this tree, it will select randomly one variable and it will try like split. And maybe this variable it's meaningless. So maybe this variable it's not really performing well to separate your point samples, but it will create this node, pass to another level, and select other variables. So maybe you could have like a really deeper trees, but it could help. So it's difficult to predict it. So you need to really think in some parameters, think about how, what are your computational capacity, and think in how you will do the predictions, because I don't know, maybe we can have a random forest with 1,000 trees, but how we will run it, we have a server to do it, or maybe it could produce a very long computation time. So you need to balance all this to define this grid search CV. So it's why I really like to not using that. There is one strategy that you just put some random value between like one range. But I think it's nice to if you think about it and really try to put some values that are specific for your domain, for your problem, and for your application. So mainly here, what we are seeing is all the, so you can see that there are 18 candidates. So it's mainly 3 multiplied by 3, and so yes, 3. Why it should be less? So 18, yeah, 3, yeah, 3 by 3, 9, yeah, multiplied by 2, 18. So actually, if you think in all these combinations, you have 18 combinations of hyperparameters. So it grows fast. So I don't know, if I put like more 2 parameters here in each of these options, it will be more than 100 combinations, and you can quickly blow the process. Not here in our case, because it's a small data set, but mainly for all these 18 candidates, we are using a 5-fold cross-validation strategy. And so actually we are training 90 models. So, and here you can see the result of the F1 score, weighted F1 score for each of these combinations. And here we are optimizing it by the higher value. So, and the best parameter is this one. So maybe we could optimize a bit more, but for this data set and for the random forest, we can put more trees if that was maybe that could help, but maybe not too much. So, and yeah, I think this, yeah, I think here we stop for a break, and I will back for the second part, and we can analyze better the probabilities and predict other years. So, and there is, I don't know if there is questions. There are questions. Not in the chat. So, okay. So let's have a break, and we're back in half an hour, right? So, hi everyone. We are back. So, yep. So I will do a short recap of what we are doing here before to proceed with the new ways to implement it. And now we have like more time to go in deeper in the code and see and interpret the result. So, and we can discuss some some other aspects. So mainly we did everything here we did using the random forest. So we implemented a hyperparameter optimization, and later we used the hyperparameter optimization to find the best model and classify the probabilities. So to produce the probabilities. And so before the break, I was explaining that here it's mainly the different combinations of hyperparameters that you can set here. And the best one, and it's actually used to calculate like the evaluation metrics and the random forest. So, and one thing that one important aspect here, so you can see that mainly there are three processes here. Like one process is derive find what are the best hyperparameters and how using this evaluation metric. And here again, this is the F1 score in this case. And so using this best parameter, it calculates the evaluation metric. So now considering this, it will run again the five-fold cross-validation. So it will split the points in 5 different groups, and it will use each of these groups as validation and train with the other 4 groups. So at the end, you will have like 5 models, and these models will be used to predict different parts of the data, and you can have like a result for your for the classification currency, and you can have like all these metrics. I will explain a bit about it. So, and mainly you can see that this is to calculate the evaluation metric. So it's mainly execution of the cross-val predict method from the scikit-learn. So you send the data and you receive like an expected value for all your samples, and these values were are predicted using like the out of fold. So it's a proper way to generate to generate like predictions, and you can compare it. So you can generate metrics about it. So, and I will show to you specifically the method that we are using here. So mainly we are using these methods here. So it runs inside of LandMapper. You don't really need to worry about it, but it's nice to know, because in the user guide you have like a good explanation of how it runs. So it's mainly like a cross-validation strategy that will predict all your samples with a valid value for derive your accuracy metrics. And so, and after that, after the evaluation, you can see that it trains a random forest using all the samples. And why it is important? It's mainly because for the evaluation metric, you have like the land mapper will train 5 random forests because we need to have 5 models to predict different parts of data and to provide like a proper cross validation. But at the end, we want to have like the most accurate and precise model. So we are using all the samples to train like the random forest. So all this approach it's implemented here. So first there is a evaluation, the calculation of the evaluation metrics, and later it will train like the final model. And this model, it's actually what you save, and it's what you use to predict. Because the assumption here is as you are using all the points to train one model, it will be like more precise, or it will have a better accuracy than the models that you use to calculate the evaluation strategy. So, and this everything, it's in, all this workflow, it's implemented here inside. So what I will show now, it's if you look the confusion matrix, so all these metrics, they are mainly derived, all the metrics actually, they are derived from the confusion matrix. So if you have the confusion matrix, and if you have the expected and the predicted result, you can derive all these metrics. So mainly the overall accuracy, here it's a classification accuracy, so it's a dominant class. And you can see that the overall accuracy, it's mainly like how the model it's predicting right all the classes. So it's like here you can see that the mixed forest, this is the expected result, and this is the predicted result. So considering all the points available, 37 points were predicted correctly. And if you sum all these values here and divide by the total number of points, you will have like the overall accuracy. But this is just like a overall metric. It's a lot more to have a general view of the performance of the classification. It's better really understand each metric. So if you look here, for example, you can see that we have like a 63% of overall accuracy, but some classes are performing like really purely not well, right? 6 here. So and you can see that these values here are really like it provides much more information about which class are better or not. So okay, and let me show I will go back to the metrics here. I'm trying to find there's a link here with scoring metrics. So, and inside of each this metric you have the precision here. You have like how it is calculated. So it's basically a rate of the true positive divided by the true positive plus the false negative. So, and these are really like standard metrics for machine learn. And I think the best way it's to understand these metrics is it's really like looking the confusion matrix and calculating it over the confusion matrix. So it's a nice way to understand what they mean, and because it's related with the error of commission, how much the classification it's C more than it is. Like, for example, if you have like a pixel that it's not pastury and you are classifying as pastury, so it's more like a commission error. And if you have like a pixel that is a pastury, so in the reference data it's pastury, and you are classifying like other class, it's omission error. So you can work with this class and understand better the performance per each class. So it generates how you can understand it better. But if you think here, we are just talking about the dominant land cover class. So because a pixel, it's more like a exclusive type of classification. So a pixel can be a pasture or a forest. So it can't, in a hard class, it cannot be like both at the same time. So when you work with probabilities, these metrics, it's kind of doesn't make sense, because they were conceived considering this main assumption. So a pixel, or in this case, a pixel can be just one or other class, not both at the same time. And if you have a probability result, you can have both at the same time. So to illustrate it, I will open here all the probability results. So you executed all the so you can see the results here. So I will open directly in QGIS, it's better. So raster. Here you can have the hard class. And let's sort it. And yep, I will put here. And now you can, let's put some nice colors here. Yeah, I will use like a range of 0 to 50. So now we can see that here. So you can see how the probability it's changing. So, but what I would like to show is this. So let's get one region where we can have like multiple values. Yes, so and let's check the class here. So mainly these are the class. Yeah, there is something wrong with this list, because it should be ordered. Because you can see here that mainly it works like, actually this is the order. So 0, it's the first one, second. So this is actually the order here, the expected order. So probably, yeah, we need to have this. So here we have all the unique class, but inside of the land mapper, we can have this is the target class, but I also have like the labels. So I will just get it in the documentation. Yes, the target. Here in the beginning. So yeah, here we have the target transformation. Yeah, so we have this target class. So here we have the original and the so here we have the same object, and you can see that these are the class that we have in the original data set. So this one, so mainly what I will do here is let's get our points. So we have the points tile, and we have this column here. And for this column, we can get all the values and organizing it. So class list. Yeah, these are the labels here. These are the class. Let me just match this order and we can see. Label. Yeah, for the sake of time, I will just use this because we need, this is just, we are trying to match it with the, because here you can see that it's not right. Yeah, so I will basically hard it. Yeah, so the right order, it's actually this one. So this is the first class. This is the second one. Because the land mapper, it actually follows the order of the original class. So it's just a matter of remap it. But here there is like a bug to do it properly, just to present, not to predict. So in the way that we have now, so you can see that it's just now these are the right class. So the first one is industrial area. The second one is this, 3, 4, 5, 6, and 7. So, and these are the class that we have. And again, the land mapper actually starts from 0 because it, for the XGBoost that we will present, it actually, you need to start from 0. So it's, I prefer start the mapping the class beginning from the 1, but when I was preparing the training session, I got this problem, and I modified the land mapper, and it's why you have this mismatch with here it's band 1 because it's the first band of the raster, but actually the predicted value is this guy here. So what I will do now, just to provide a better way to analyze the result, I will rename it. So this is the first one. So you can see this is industrial and commercial units. It's more related with the urban area.
Is it very hot?
Yeah, it's working. You can see here.
Okay.
So this is the second class. This is the third. So maybe a nice functionality would be really write the files in using like some description column that we have in the inside of the data frame. So this is a nice, could be a nice improvement here. So, and broadleaf forest. Yes. So now you can see that This is actually the coniferal forest. The pasture areas, the industrial and commercial units, so it's more related with the urban areas, the broadleaf forest. And so, and for example, if you get like this pixel and this, so this is no irrigated arable land, you can see that this picture, you can have a bit of confusion. And if you check it here, so you have 53% of probability to be no irrigated arable land, but 31% to be pasture. So in this case, you actually, you have, you can have multiple class in the same pixel, and depending of your application, you can play with these probabilities. So maybe if I'm interested in pasture, this probability it's enough for me, and I can use it to classify this picture at this pixel as pasture. So the nice way about these probabilities is you really have the flexibility to work with that later. So this decision to what value you use to separate and to define the dominant class, you can do it later, and you can do it specifically for one class. Maybe you are just interested in forest, so you can use all the probabilities available for forest and things like that. So, and because of this, so it doesn't make much sense thinking accuracy, because you are working in the probability space here. So, and it's why we use it the log loss metric here. And this log loss, you can see how it is calculated here, but it's mainly the difference in the probability space with the expected result. And if you think here, the expected result, we are using hard class to do the prediction. So mainly we have like one pixel in our training sample, one pixel it's just pasture, or it's just agricultural arable land, or no irrigated arable land, or it's just forest. So we are using, inside of the land mapper, we are using this class called label binarizer. So it's just a way to convert all this data, hard data, in a probability. So it will be like 100% of probability for the class that we have, like pasture and the training sample, and 0 for the others. So the log loss, it will calculate the difference between this expected result, 100%. So if the models achieve 100% for that pixel, it's a perfect prediction. And that's not the case for the most part of the pixels, because we have confusions, and we have problems with like to generalize. And if you are predicting everything perfect, probably your model is overfitted. So, but you will have a difference. So in the log loss, if you have a lower log loss, your prediction is better. So because you have less confusion between these the other class. So for example here, it will be a higher log loss, because you can put the other probabilities, and if you turn all the probabilities, you actually can see the log loss. It's just like a metric to evaluate how much difference you have in this probability. So if you have like 20% in all the classes, you will have a higher log loss. Compared to that, for example, maybe this pixel is just mixed forest. So, but we are using it because it's a nice way to evaluate the predictions in the probability space. So that's the main reason. And you can see that it's why we implemented it here, and we sent to the land mapper, so to the to do the hyperparameter optimization. And here you can see the values are different because we changed the metric, and the lower value, it's best here. And you can see that it's a different parameter. So if you go back here in the random forest, I think it's different. Yes, it's different. So because the maximum depth here, it's none. So the trees will grow deeper and to separate all the class, all the samples. But here we use it like a tree with just 5 levels of depth. So that's nice because we did the same thing, the same approach, and we just changed the metric because now we are using a proper metric for the probability classification. And mainly we are using a different parameter. So, and here, for the probability space, you can actually now, if you think that each of these maps, because you can see here in the QGIS, you can see the class, and mainly if these values will sum up 100%. Sometimes it doesn't work like that because you have some problems with the, here we are writing the data as byte format, so between 0 and 100. So in some cases you can see some mismatch between the floating point, but in general you will see like all the probabilities will sum up 100% because it's the way that random forests it's dealing with this type of output. But if you think for your kind of application, you could, I don't know, just get one map. So I will get, for example, here, just the forest one. I will close it. And so I have full flexibility to define where would be my forest. So it's a probability layer. So I can came here and just, I will just hide all the values bigger than 50%. And so, yeah. Here we are just seeing like, maybe I was too strict, but I'm seeing just pixels where I have like 50% or more like with probability values, and you can play with that. So you have full flexibility to define your probabilities and work with the data with the way that you prefer in your domain or in your application. And there is this nice metric specific for the probabilities where you can calculate like what would be the best probability value considering the like all the possible thresholds. Because if I specify like 30% as threshold, I will see more forest than 40%. So you can test different, what this metric does, it's mainly test different different thresholds and use it to estimate what would be the best cutting point. And here you can see that the cutting point that I'm specifying here, it's this optimal probability. So if you use this probability, you will receive like these two values. You will achieve these two values in the precision and the recall. And you can see that it's a balance. So your map will like, it will have no bias. So you will not see much more pasture than exists, or you will not overestimate or underestimate all these classes here. So it's one way to use it that we implemented here, but it's for sure it depends of your application. But what it's the main message here, you have full flexibility. So it's why it's important to provide these probabilities. So what we will do now is, so till now we just worked with the random forest. So now we will really use more than one learner and implement mainly this workflow here. So the land mapper, it supports a list of learners and a list of hyperparameter optimization. So what we will do is we will train out 3 learners. One, it's a random forest, as we are doing. Other is the gradient boosted trees, and other it's a regular artificial neural network. So we could use other learners here, but these 3 learners were the best that we found in our internal benchmarks and tests. And for example, you could use SVM, but sometimes this learner, it's really like high computational. So to do prediction, it's not really operational approach for us. So considering these 3 learners, all these learners will predict probabilities. So we will generate probabilities using the gradient boosting trees and the artificial neural network also. And we will combine all these probabilities and generate what we are calling here as meta features. So we will use the probability to train a second layer of machine learning. And as it is a second level, so you can think that the original features, the Landsat data that we are using, they are the input data here. And we are generating the probabilities, combine them, and training one more learner. So it's a kind of meta feature. So the probabilities are actually here a derived product of the original features. And we will use just a logistic regression approach here, and we will provide the same output, the probabilities, the dominant class, and the uncertainty. And if we think in the uncertainty, it's a pretty nice way to generate it, because now we have random forest, gradient boosting tree, and artificial neural intelligence. So each pixel we have multiple predictions, at least 3. And the uncertainty here, it's mainly the standard deviation of the probabilities. So if you think that maybe one pixel was classified like with 80% of probability in all the 3 learners, so we will have like a lower standard deviation. So it means that the 3 learners are agreeing, did agree with this prediction, with the output of the class. But if you have like random forest predict 80% and the other learners predicting like 30%, so we will have a higher standard deviation. So it means that that pixel, it's more tricky because the other learners are not able to deal with that. The problem is you really need to use like comparable and strong learners here. So for example, if I put like a poor model, maybe it will overshoot, or it will mess up with my uncertainty, because I can use like a I don't know, just a linear regression or some like weak learner that doesn't provide a good occurrence. My uncertainty will be compromised. So it's really important to find what are the best learners available, and in our results we found it. So gradient boost, it's what the literature says, artificial neural network and the random forest. So, and if you think in this ensemble machine learning approach, you have this nice framework here implemented in Python. And there are different strategies to combine it. So you can put like multiple learners, you can create several, you can combine all these probabilities in different ways. But mainly here in the EU map, we didn't use it. I'm just put here because maybe it's a nice way to understand better this concept and how it's implemented in Python. But we didn't use here because it's really this framework. It was optimized to not preserve all the intermediate results, and we would like to have access to the probability. So I will show to you after the predictions. You can have the probabilities of the random forest, the probabilities of the gradient boosted trees, and the probabilities of the artificial neural network. So we can derive each probability separately, and inside of the land mapper, it's important has these probabilities because we will calculate the uncertainty over these probabilities. So here we just use it like a regular cross-validation prediction in the EU map. So, and each of these three learners, we will also provide a hyperparameter optimization. So it's a robust approach, if you think, and you can use more, you can provide, for example, feature selection. We will not cover here, but in the EU map, you have a tutorial to explain it. So it's a nice way to, you can use, you have like really flexibility to implement different pipelines and different workflows for your application. So here we will create the random forest using the same parameters. Here we will create the XG boost. So, and you can see for the XG boost, I'm mainly using these two parameters. So each of these learners, they really have, you need to understand what are the parameters to provide a nice way to optimize them. So it's not really simple. You need to read about the method and the algorithm. But for example, here in the XGBoost, you have a lot of information about this gradient boosted tree. And this library, it's really compatible with the scikit-learn. And for the artificial neural network, we are using the Keras classifier. So, and you can see this is a TensorFlow class. So you are using, here we will use this to build like a neural network just with some fully connected layers. So we are calling it like, in the tutorial, we are calling it as dense layers. So it's just this layer here from the TensorFlow. But in the, let me show to you, in the UMap, we are using this method. So basically it's a dense layer, so a fully connected neural network, a dropout layer, and a batch normalization, and it's just like several layers of this combination. And you can see here that I'm using this pipeline in the scikit-learn. So with the pipeline, you can combine different operations inside of the scikit-learn. So mainly I'm normalizing all the data to optimize the training for the Keras classifier. And I'm calling the Keras classifier, sending like a function to build the network. And here I'm sending all the parameters. So you can see that it's just 5 epochs. So it will train using the whole data set, using just part of the epochs. And Actually, one epoch will use all the data, but here we are using just 5 because if you put 50, 30, it will take more time, of course. And here it's the number of layers. So actually we have like a dense, a dropout, and a batch normalization. So we have 4 layers of this combination. So and this is just like a helper to create a regular artificial neural network in the QGIS classifier. And here we have the same object, so grid search CV, but with a difference. So you can see that we have the estimator, and this the same name here, and we have this double underscore, so it will indicate to the scikit-learn that these 2 parameters needs to be optimized. So I will test mainly 4 neural networks here, one with dropout rate equals 0, and other with dropout rate equal 0.15, and with this number of layers, so 2 and 4. So it's mainly it's kind of creating this, calling this method here with different structure for your neural network. So it's a nice way to provide this, test different architectures inside of the TensorFlow. But again, this is just like a regular neural network. It's not a deep learning. It's not a convolution neural network. It's a pretty regular one. And so what, till now, we created these 3 objects: the random forest, the gradient boosting tree, and the artificial neural network. And now we will create the last learner, that it's actually a meta learner. And this learner and this model will receive as input the probability values. And we created it here, and you can see in the documentation there are some options to implement the to select the solver. So it's how the linear model will be fit inside of the implementation. Mainly here we are using this SAGA solver because it was the fast one that we tested, but maybe it could depend of it depends of the probability values for sure, and it depends of the data that you are working. And again, you can see that these parameters here are really you can put different values. Here we are just testing some specific parameters to train and to fit this linear model in a different way inside of the scikit-learn. So one thing that I forgot to mention is this. So if you open, for example, I will back to the documentation. So this hyperparameter optimization, you can see that we are defining the fit, intercept, and the C. And these parameters, they are actually the same one in this learner documentation. So you can optimize any kind of parameter that you have here. So for example, if you want to optimize this class weight, you can just copy to here and define like which values you will optimize, and it will increase the number of possibilities. So you need to be aware of that and careful, because could improve a lot the computational time. And now we will keep the same structure. So we have the same points here. We also have our cross-validation strategy, and we have the feature column prefix, so all the columns that we will use to train the model. And we have the estimator list and the hyperparameter selection list, and this is different. So you can see that now you are sending to the land mapper a list of learners and a list of hyperparameter selections. And of course, you need to match the order of the hyperparameter selection with the order of the learners. So now, instead to just use one estimator, one learner, it will use several implementations, so several learners. And this part here, so all this workflow will run inside of the land mapper. So you can see here, and now we will do the training. So you can see that the first part is it will optimize the parameters, the hyperparameters for the random forest. So it will show all the combinations as we already saw, and now it will optimize the XGBoost classifier. So now it will test a different learner with the informed hyperparameters, and it will do the same thing and find what are the best parameters. And you can see here, this is the evaluation metric, the log loss. So as we are aiming to predict probabilities, it's the best way to optimize the hyperparameter optimization, to do the hyperparameter optimization. And now it's doing the TensorFlow. Let's see how it works. Yeah, I almost without RAM here. So it's running the Keras classifier, that it's actually a TensorFlow class. I think the whole workflow for this takes like 2 or 3 minutes, something like that. So now you can see that it tested these 4 combinations, and this is not like, it's just a demonstration. To do a production work, you need to use more epochs. So it's really important for the artificial neural networks. But you can see that you have the log loss for the random forest and for the XGBoost, like the gradient boosting trees, are close, but for the TensorFlow, not so good. So remember, a higher value for the log loss, it's a worse classification. And so now, if you think that we have 6 class, so let's go back here and see that we have 6 class. And here, or this. Yeah, actually we have 8 class, sorry. And so each of these class will have a probability value from each learner. So if you think we'll have 8 probabilities for each learner, and we are using 3 learners. So the meta feature is it's actually a combination of all the probabilities. So we put together the probabilities of the random forest, the probabilities of the gradient boost, and the probabilities of the Keras classifier, the artificial neural network, and we created like 24 meta features. So actually they are derived from, they are actually the probabilities, but for a new learner that will use it, now we will train a new model using these probabilities as input. So we call it this approach as, we are calling here as Ensemble machine learning, but in the literature you have some works to refer it as super learner. So actually we are training a new model that use the probability as input to predict and to improve the accuracy of the result. And you can see here that it's doing a good job. So this is just a logistic regression. It's basically a linear model. And you can see that the log loss, it's lower than all the learners, what is expected. So because we are training a new learner that you use these probabilities as result. And now we have the land mapper calculated the evaluation metrics, as you can see here. And now it trained over all the 3 models again, but now using all the data. So the full history of the processing is here. So it trains the random forest, optimizing the hyperparameter. So this is the best hyperparameter in our list to achieve the lowest log loss in all this hyperparameter list. And the land mapper do the same thing for the gradient boosting trees. So, and you have like the lowest log loss here again. And he's doing this, it does the same thing for the Keras classifier. So you have it. So the first part, it's really the hyperparameter optimization for all these 3 learners. And later it put together all these probabilities as meta features. So now we have 24 values, 3 learners multiplied by the number of class that we are using. And we fit a logistic regression using it as input. And the last part, it's just train a random forest, gradient boosting tree, artificial neural network using all samples. So because we already did everything, and like all the evaluations and all the hyperparameter optimization, and train a meta estimator with all the samples. So the complete workflow, this worked, and as output, let's see the output here. So you have a better log loss, and this is just the training. So now we are ready to do the predictions. And so to do the predictions, it's the same approach explained by Chris. So you need to retrieve all the raster layers that you used in the training part. So you need to retrieve the DTM layer and all the Landsat bands. So this function, this code here, it's just to access this data in the folder that we are providing and matching the name. So removing the year, because in the original, in the training data, you don't have the year because you have points from multiple years. And mainly here you can do the prediction. So it's the same approach. And now I'm just calling like a different, I will use a different name here. And you can see that it's first it executes the random forest, later the gradient boosting tree, and for last it executes we are calling the pipeline, but it's actually like 2 operations. One, it's the normalization of the data, and other is the Keras classifier prediction. Let's see how it works, how it's doing the processing. Yeah, it shouldn't take too much. Maybe I need to free some of the memory here. Okay. Yeah. Now we have it. So when you can see that the same bands were produced, the hard class, and now we have the uncertain layers also. And this uncertain layer, it's just the standard deviation of the probabilities that we predict which using each learner. And now let's open this data. I think it's a good exercise if we compare it with the random forest. Okay. So when I will organize these layers here, and I will use like human readable class names. Here, okay. And now we can compare, like, so this is the pasture area, and you can compare with the I will copy the styles. So here it's more restrict. And this data is from 2018, right? So this is the coniferous forest. And we can also compare the hard class. And for the rare hard class, I will just use some colors here to help us. And I will open the uncertain layer also. And this is the uncertainty layer. And you can check the values here with so you have this is the kind of the standard deviation for the probability values. And that's one of the main advantages to use this approach. You can compare, you can generate this uncertainty using different models, and you can put more models, would be better, but again, it depends of your end goal and your application domain, because you need to have a model that will be used for real predictions. And here you can save the same. You can save the model. So as we presented earlier, you can really use the model to do predictions in the future without retraining it. Yeah, so this is just like we executed the 4 examples that we planned, and yeah, we have time now in the end of the session, so we can discuss some of the aspects that we presented, and we can test for the other tile, and we can increase the number of points. But yeah, now I think we can use this time to discuss about what we were talking here and the examples that we presented. Okay, any questions? Not in the chat.
I have a question. What do you think would be the next thing to add to this kind of functionality?
Specifically to the land mapper?
Mm-hmm.
Yeah, I think we can definitely improve, like I think we can improve the output now. So it's something that even here during the training session, it's difficult to match the probability layers. So for example, because you have like a value here that it actually doesn't match with the original values in your class. So we could add like a functionality to improve the way that we are generating this output, and maybe we could support other type of structure for the super learner. So for this, because now we just have like 2 layers, maybe we can put other different topology. I don't see like much value on it, because if you put a 3rd learner here, it will not add too much to your classification. But so the rest, it's here. So for example, if you want to do a feature selection, you just need to implement a pipeline and send it to the land mapper. And so it's fully compatible with scikit-learn. So you can use different models and different approach. So it's just a matter to really use this pipeline, that it's a nice way to integrate all these workflows. But of course, I think it would be nice if we have more users and to start using this code to other applications, because we are developing it. We were developing it like in the last months, and we are fixing it and try to add new functionalities. But maybe for some other applications, we could implement a different functionality that, for our case, it's not really important now. But yeah, a short answer, it's definitely the way that we are generating the output. I think this must be improved, because we are producing too many layers, and it could be better explained to the final user, I think.
Do you have any functionality proposed? Do you have the finishing map nodes and
Yeah, you mean like after the classification, do some post-processing?
yeah, because you can still have
Yeah, that's a good point. That could be a nice functionality, because of course you can do it outside, but if we put like a post-processing method, we can implement some of them in the land mapper. But now we don't have. I already use like this one. So in the SciPy, you have some kind of ND image and the image and the array median. Yes, this one. So this is actually like a median filter, but it works like on multi-dimensional data, not this one, it's the filter, this one. So this is nice because, for example, you can, so it's just a median filter, but it works on 3 dimensions. So you can actually create like a cube kernel, like with, I don't know, 3 by 3 in the space and 5 window, and you replace the center value with the median of all this cube. And this could be one of the ways to do post-processing. I did it for the pasture maps that I show in the morning, that I did show in the morning. So, and you can just work in the space. For example, you could try run like a smooth filter over the probabilities. So this guy here, this SciPy, this has also like Savitz-Golay filter. So yeah, so you can use it over the probability because it's a NumPy array. So definitely that could be a nice functionality in the package, like inside of the package.
But like then there is a so once you have this like finite map, there is a possibility of accuracy for your accuracy points falling into after you have finalized it, then it can again affect the accuracy of your map.
Sure.
Then
yeah, that would be, for me, that would be the right way to do, because now, for example, we are just providing a cross-validation strategy, and if you change your pixel values, you will have a different map. So and for the cross-validation, Yeah, I don't know if it would be possible apply the filter before to calculate the metrics. Probably it would be, but it's to really, for me, a proper validation really needs to use like independent data set, as you mentioned.
Because like now it's giving you the accuracy of the model. What about the accuracy of the map itself?
Yeah, I agree with you. Like, but you need to find independent data set, independent point validation, validation samples, and so, and at the best way, like if you look in the literature, the best way it's really create the map, and after that, using this map, you can use the class that were predicted to create a sampling design, like a stratified random sampling. So inside of each of these class, you just spread points and you inspect these points, because we are talking about land cover. So if you have like the Landsat data available, you can check the points and see this is forest, this is not forest. Some classes are tricky, so it's difficult to distinguish like mixed forest or from coniferous forest. So it depends of your legend also. But, and after that, with this independent validation, you can back to the map and just do like a proper validation. And it would be, so the reference here, it's the capability and the capacity to the a specialist check the image. That's work, for example, for the land cover, but for soil organic carbon, no. So you can do the predictions, you can provide the maps, but to do a proper validation with the dependent data set, maybe you need to go to the field, and there it's a kind of, it's difficult to find the budget and to find the time to do it. But for sure, it's more reliable, I think.
Yeah, I'm talking from my personal experience. My model would give me 95% accuracy, but when I do accuracy from independent data, it falls to sometimes 70%.
Yeah. And how you are doing how you are getting the independent data set?
So independent data set, so in this picture, what you can do is Landsat, so you can always go back to a data set that's higher resolution than Landsat, so you can use that using vision. If you are not, obviously, if you're not working with like data set, that's not
yeah, that would be nice for some of this tricky class. So actually, you can provide the sampling design, and imagine now here we are using like we are producing a land cover product for 20 years, so since 2000. So if we spread, I don't know, 500, 1,000 points all over the Europe, we can have like a pretty good occurrence assessment, like a validation, and we can analyze these points in the Google Earth and in the Google Earth images. And so, and it would be easy to identify the most part of the class, like vineyards and mixed forest and things like that. So, and of course, you are generating like a better, because in general, you need to use a better data to do the validation, and that it's the case here. Okay, let's see the chat. Oh, okay. There is a question here about the, yeah, there is actually two questions here. One, it's about the hyperparameter optimization. So yeah, it's possible. You can change the grid search, but I don't know what are the options here in the scikit-learn. I actually tested a few, but I always prefer to define it. But you have, yeah, you have all this. So you have this random search CV and this halving grid search. I'm actually not quite familiar with them, but we are calling the cross val predict method from the scikit-learn. So I did test with the random search for the CV, and it worked. So you can use like any of this scikit-learn implementation, you can use it here. So I don't know, you can get this random sampling and just import in the, you can just import like, I'll do a, so you can just import it here, and of course you need to define other parameters because here it's a param grid, and you can use it and instantiate to define the range, right? With the random search, you need to define like a range and for each of the parameters, and you can send this to the to the land mapper. So it should work, considering the current implementation. Like about the concept of aspects of it, yeah, you have different ways to implement hyperparameter optimization, and of course it's tricky because sometimes you need to use like some strategies to optimize it, and but mainly I like to I prefer use this grid search just because it forced me to think in what could be the best values, because and it's more like a personal thing for me. I like to try to understand this algorithm and think what would be the best hyperparameters considering my problem. So a good example is this probability. So if you think how the random forest works for the probabilities, so it mainly use the leaf node, the end members, the end node of each tree to derive the probabilities. So if you have like shorter trees, like with less deeper trees, probably you can have better probabilities. So because if you grow everything to the end, so the leaf node will have just like a few samples. So it's nice to, maybe you could try to optimize it like the maximum depth and define what could be the best values. But of course you can do this exercise with other heuristics or other implementations. So for the grid, for this maximum depth, I can, instead to just establish the fixed values, I can use some heuristics or some random approach to do it. So but inside of the land mapper, it should work fine. And the other question was related with the cross, the spatial CV. So actually the land mapper, I think Chris talked about it, but the land mapper, you can find this column group CV call. So here it's mainly the column that will be used to do the spatial cross validation. We are using it in the project. So for example, in this case here, if you split this tile in different grids in different cells, and you overlay it with the points, you can provide like one tile ID, like one region ID, blocking ID for each of the samples. And you just need to inform this column for the land mapper, and it will work. The downside of it, yes, you need to do the blocking tiles outside. So you need to have like a vector of it and calculate it by hand and use it as a tile ID. So probably that's something that we could implement inside, because you can, considering like an area, we could implement it inside of the land mapper to create automatically this blocking vectors, overlay it with the sample points, and use it to do a proper spatial cross validation. So now you have support on it, but you need to manage the blocking overlay and define the blocks, the size of each block and things like that outside of the land mapper, as we are doing, for example, with our own tiles in the area of the project. Okay. So let me see if we have more questions here in the chat. And yeah, I think the last thing I really would like to show is, so again, we are, this package it's really under development. So what the goal here is really put available all the tools and functions that we are using, approach that we implemented in Python in the context of the open data science. And it's really like we are working like in the last months we worked a lot, and so we fixed some bugs, but for sure there are some problems, and we are really working to optimize it and to create a better library. So what would it's nice, it would be nice from you, if you really plan to use it, if you find any problem, you can create just a new issue here and describe your problem. I need to log in here. So yeah, okay, it's working. So you can really explain what the code did you executed and what problem did you found, and we can fix it. So we plan to, the plan is really maintain it and adding new functionalities and providing better like ways to manage and to deal with the data. So we will implement new gap filling approach. So we have a class, for example, here in the API reference, we have this class so this class access automatically the GLAD Landsat product from the University of Maryland. And you can see here that you have a code, this code, it runs if you have the username and the password. So it's a nice way to retrieve, for example, the raw product from the University of Maryland. We already did it, and we are providing here in the EU map the composites per season. But I don't know, maybe you are interested in work with the 16-day composites and you prefer process yourself for a specific area. So you can use this functionality to read the data, and it will download the data and directly read it as an NumPy array. So we will not show it in the next sessions. The focus will be more in access our data, but you have this functionality here, and you can see there is also like the percentile. So this is actually the same function that we use it to produce the mosaics per season. So, and here the plan is really put new class to access this data, the other data, not specifically this one, but this harmonized Landsat and Sentinel product. So we will keep increasing the library and adding new functionality. So if you start use, please just help us to improve it, creating here a new issue if you have an idea or functionality. So that is the point, the whole point, to show and to present it to you. And yes, I think, and that's all for today. I would like to thank you, everyone. So that followed us here in physical and online. So, and we see each other tomorrow. So we'll have more sessions tomorrow about how to access the data, and in the afternoon we'll have the GRASS workshop also. So thank you a lot.
Thank you.